All right, so in the previous video, I actually derived this expression for FIFE, the final initial final E, which is used to determine the voltage across the capacitor with respect to time, or as time passes in an RC circuit, okay? So let me go ahead and just copy this. We're going to take it over to the next slide with us. We'll come right here, and I'm going to define, sort of overview the charging and discharging cases for RC circuits, talk about what that means, talk about this expression and what it tells us. And I might have to break this into 2 videos just because it may take a little longer to define. Yeah, probably we'll do a charging video and then a discharging video. And so what I mean when I'm saying charging and discharging, it defines what's happening to the capacitor in my circuit. Okay, so in the circuit in the previous slide, I drew a voltage source that's going to pulse from some low voltage to some higher voltage. I could say 0 to VC final. It's going to start at 0 and then it's going to go up to some final voltage, which I said would be the final voltage across my capacitor. And this would be C. And what I'm interested in is, what is VC of t? What does it look like, right? If I were to plot this voltage with respect to time, what is the plot going to look like for VC of t? Okay, that's what I'm interested in. And so for a charging circuit, what I'm saying is my capacitor is initially discharged. It's basically got 0 voltage across it to start. And so we could write that as an initial condition, that VC of time t equals 0 is 0 volts. So everything leading up to time 0 is going to be 0 volts. Let me actually draw that in blue. So I have 0 volts. And then at time t equals 0, I have this pulse, right? My voltage here pulses from some low voltage up to some high voltage, VCF. Okay, and when that happens, what my RC circuit does is it charges up exponentially and then it flattens out to that final value. And that's what this FIFE expression describes, is it describes that behavior. And then these final and initial values really just define where those things happen on the time axis and how high does the voltage actually end up, okay? And so, like I said, it's going to end up at some final voltage, VCF, which is equal to this VCF. Whatever that source voltage pulses up to, that's the final value. So my capacitor is going to just charge up just like this, and it's going to flatten out and asymptote right here at VCF at some time t. And so what we're interested in is how fast does this exponential growth happen, and where does it really reach its final value? Those are the interesting questions for RC circuits. And so what does this all have to do with the FIFE equation? Well, the FIFE equation is the general equation for such a circuit that tells us this exact behavior that we're looking for. Okay, so let's examine it. If I throw my FIFE equation here, I say VC final plus VC initial minus VC final times e to the negative t over RC is equal to VC of t. Okay, so this is the general form of VC of t, which is exactly what I said I was looking for, right? That's what I'm looking for. And so if I know that this is a charging circuit, which I do, I'm on the charging side of my screen here, and I would always tell you something that would give you a hint as to whether or not it's charging or discharging. Whether I specifically say it's charging or I give you an initial condition like the voltage is initially 0, then you know that the capacitor is charging, okay? And so if my initial voltage is 0, then I can send this VCI term to 0, and what I'm left with is VCF plus 0 minus VCF e to the minus t over RC, or I can factor out a VCF, and I get 1 minus e to the minus t over RC, okay? And so this right here is the expression for a charging RC circuit, because I've put in my initial condition that the voltage across the capacitor is 0 at time t equals 0. And then this expression would give me this behavior right here. That's exactly what this expression would give me. It's going to say that at time t equals 0, if I put in a 0 here, then this whole thing would go to 1, and this entire thing would go to 0. So VC of t at time 0 is equal to 0, which is exactly what we see here. Well, at some time much, much later, T is going to be huge, and so this entire term is going to basically go to 0, and I get just VCF, which is exactly what this expression tells me, that at some time much later, my voltage across the capacitor is going to just be VCF. And then all the times in between there is this exponential behavior leading up to that asymptote. Okay, so that's what's happening in the charging case. In the next video, I'll talk about what's happening in the discharging case, and I think it'll probably make a lot more sense now that I've gone through the charging case.